Welcome back again to the course on Design Compiler Basic. So yesterday we have seen in the last class we have seen that how to set the attributes. So that means how to set it, how to group this, how to ungroup this, all these things we have already seen. So in the next we will see, as I said, that based on the specification we can put the constant to the DC environment, that if my clock speed that will be 100 megahertz, so my clock period should be 10 nanosecond. So clock period should be 10 nanosecond, that I can put as a constant to the DC environment, so that it always try to maintain the corresponding critical path that should not be more than 10 nanoseconds, something like this. So this is timing informed, that means timing budget. So same like area budget also we can as a constant we can put. The power budget also we can put. Okay, so what are the constant files are there which we can put to the Synopsys environment, DC environment, that are these things. So maximum transition time, Fanout, capacitance, that can be done through set underscore max underscore transition, set underscore max underscore Fanout, set underscore max underscore capacitance. That means these three commands sets the maximum capacitance value I can set, maximum transitions value I can set, maximum Fanout I can set. So this, like the same way, the cell degradation also we can set by this set underscore cell underscore degradation. Then minimum capacitance value can be set as set underscore min underscore capacitance. Optimization constant, how we can set? Area wise we can say that set max area that should be this much. The speed wise, clock, create clock, that means for creating the clock, then set input delay as this one, set output delay as this one, set maximum delay should be this one, set minimum delay as this one. So these are the commands which we can set as a constant to the DC environment for speed requirement. For power or leakage power or dynamic power, that means requirement, how we can set? We can set set dynamic optimization true, set multi VTH constant true, set leakage optimization true. So something like this we can put. So here you see some of the constant we can put only DC expert environment, and some of the that means constant we can put DC expert as well as DC topographical mode. In the both mode we can put that constant. So how we can set that maximum transition time? So we will see some of the examples and we will see how basically that comments, what are the job of that particular command and what it does basically. So maximum transition time, if I want to set as 3.2 for the design adder design, so that can be set as set underscore max underscore transition equals to 3.2 and get design adder. So here adder is the design, for that I am setting that maximum transition time as 3.2. So if I have set already the transition time, now I want to remove it. So how can I remove it? Remove at that time I have to put this command as remove underscore attribute get design. So this is a design name adder, then the maximum transition which I have already set. So specify a clock based maximum transition, that means based on, so the first example shows that this is purely combinatorial. In combinatorial circuit, how I can define the transition time. So sequential circuit, how I can set the maximum transition time. So in sequential circuit it will be based on the clock. So set max underscore time transition equals to 5 get clocks clock. So based on clock the transition will be done, which is 5. So then maximum Fanout, how can I set? Maximum Fanout can be set as I said, set underscore max underscore Fanout with the value of 8 with the design name adder. Then again how to remove it? Remove underscore attribute get ports port name with maximum Fanouts. That means that can remove the attributes for a particular ports, not all the ports which I have mentioned. So whenever in the earlier comment, whenever I said that get design adder, that means for all the ports, for all the, that means driving pin as well as the input port, it sets the maximum Fanout as 8. But if I want to, for one particular pin I want to remove it, so at that time I have to mention that port name. So that maximum fan out, that means constant, will be removed. So for the whole design, if I want to remove, so at that time the design name we have to set. That means here you see get port means for only for removing from one particular port, get design means remove it from whole design. So then define expected fan out for output port. So if I want to set a expected out, that means expected fan out for a particular, that means from the beginning I know that okay, the fan out should be 8 or should be 6. So that also I can set like this one, get attribute leave a slash n2 slash I fan out underscore load. So this will do what? This will find out the fan out load for this I pin of n2 cell of library lib a, and to find out the default fan out load set on logic library lib a. So you just type this command, get attribute lib a default underscore fan out underscore load. So that means what is the default fan out set for this lib a, that it will show at that time. So then next is how to set the maximum capacitance value. So maximum capacitance values can be set as set underscore max underscore capacitance with the name values of 3 and with the design of adder. So again removing means, so any that means constant is set, so that can be removed with this command remove underscore attribute. So that means here I am putting the attributes, now I am removing the attributes. Removing attributes, remove attribute, get design adder, then the max capacitance. So how can I that means specify, now specifying frequency based maximum capacitance in DC follows these steps in determining the maximum capacitance value, which is based on frequency. So it identifies the operating frequency of each cell. So that means if I am using 5 cells, so okay, so 5 cells, it is that based on the delay each of the cells has different operating frequency, right? So the operating frequency of a cell is defined as the highest clock frequency on the registers driving a cone of logic. So clock frequency are defined with the create underscore clock command. It looks up the corresponding maximum capacitance value for the identified frequency from the lookup table in the logic memory. Okay. So that means in the earlier example what we have seen that okay, maximum capacitance values has been set for a combinatorial circuit. So whenever we are talking about, or whenever we are coming to a sequential element, so at that time the capacitance value will be set for the clock. So based on the clock, now I am setting the what will be the maximum capacitance value, and that I am setting. Again after that what you can do, so doing this step, that means it calculates the maximum capacitance value for this maximum identified frequency for that particular library. So after that what you have to do, it annotates each driver pin with the appropriate max capacitance value and uses these values in synthesis. To report maximum capacitance in violating net, only use the report constant command as follows. That means, so based on that means different block, they have different frequency. So based on that particular different frequency, now each of the maximum capacitance for each of the path will be calculated. So each of the path of the calculated, if it is that means now whenever it is calculated, now you have to find out okay, what is the maximum one it is achieving. So how can you find out that? So report underscore constant is a command for which you can okay get the information that okay, this is the maximum capacitance value I am getting for this particular frequency or for this particular path with respect to clock. So here it shows that okay, report constant minus all violators minus maximum capacitance. That means all the paths or all the values which is basically violating the maximum capacitance value, that path it will show. So then again to report the maximum capacitance on all nets, for that you use report underscore net minus max capacitance. That means on the each of the net which are present on the current design, so it will show the capacitance value for each of these paths or each of these that means nets. So then again maximum capacitance value we have set. So minimum capacitance value, how you can set? You can set is as set underscore mean underscore capacitance, that is with this value, this high drive. Okay. So and you also can set that means maximum fan out. It is just like the same, that means there I am setting the maximum fan out. So here I am defining the values of minimum fan out. So that means suppose I have one circuit like this. So here there are two, in 1 and in 2 they are the two inputs and A, B, C are the outputs, right. So A, B, C, that is basically they are following this to that means the target is that okay, the clock period I have said as 10 nanoseconds. So C is getting 11, B is 12, C, A is 13. That means from input port to the output port. So at that time that means the you see that the critical delay which is basically violating, that is 3 nanosecond. Okay. So at that time I have to optimize these paths of which is basically connected with A. So how I can do this, that means how I can do that corresponding optimization. So first the thing is that we have to set okay, create underscore clock with the period of 20, then set critical range 3.0 to current design, then set maximum delay is 10, okay, with respect to ABC, then group underscore path by name group 1 to ABC. By this we can say that okay, these are the paths which basically violating all these ABs. For ABC or for all this we are getting the violation, but as I have said that okay, critical range is 3, so it will show only this path A is the violator, host violator. So the next is that how we can define the area. So area constant can be set as set underscore max area for 0, 0, 0, 0 is the default one, or you can set it by yourself with the values if you know. And to prioritize the maximum delay, max delay constant ahead of the maximum design rule constant, you enter the set cost priority underscore delay. So that means here actually speed, power, area, these three are the constant. So in which respects you want to optimize your design, that means you can set the priority. Okay, so priority means whether the area is your primary concern for your design, or the speed is the primary concern of optimization for your design, or the power is the primary concern of optimization for your design. So that you can set using this command like set underscore cost underscore priority minus or delay. Okay, so that means the priority is delay here, not the area or the power. So this is a combinational design example. So here you see there are 3 inverters which are connected in serial. So here there are like how there are several command which you can set, like here you see this current underscore design is top, then characterize U2, U2 is this cell name, then again the only the for the block if I want to that means focus on, then current design I can say that okay, this block 1 which is the U2 instance that I will set, then set driving cell as this one, the input delay is up to 3.3, set load as 1.3 with respect to D, then set maximum delay as 9.2, and then current design is the top. Okay. So that means I am setting only the constant to the U2, not the other 2 blocks, though the whole design is the top. Okay. So that you can set by this kind of by setting the command is like in this way. So in the sequential design example, how you can set the values, like here in sequential design element, the primary thing is that you have to set the clock first. So by putting this command create underscore clock, so period is 10, waveform is 05. 05 means that is starting at 0 and again that means the age will occur at 5. So then whenever you have to that means characterize this block, suppose there is this circuit is there. So there is the flip flop which are connected with some of the combinational block like this inverter and then again inverter, then block this one. So this is the, that means example of the script which has been used for the sequential design element. Okay, so that you can see, and that actually we will see this type of example whenever we will do actually we will work on the software itself. That at that time we will see this example. So how you can characterize multiple instances. So in the earlier two examples, what we have seen, particular U1 block or particularly U2 block. So here also in the other example, particularly let's consider one particular instance. So multiple instance, how you can characterize that also you can, that means characterize U1, characterize U2, both the things you can do, as U1 and U2 are the two blocks which is comes under this top, that also you can do. So and that means now characterizing the designs with timing exceptions. So timing exception means I have two sequential elements. So in the previous example, this is for combinatorial design. Okay, so this is for sequential design element. So sequential element means there are clocks are connected with U0 as well as U3, both it is connected. So how you can now characterize with, if they have two different frequencies, so now how you can characterize both the things under this alarm underscore block, which is the top module of it. So that thing we will see during the exam, that means lab class. So after that you have to compile the design, that means after loading, that means reading the Verilog file, then analyzing, then elaborating, then setting the constant file, then what you have to do, you have to compile the design. So that means from the generic library, now it will be converted into the target library, my design. Okay, so that's why I need this design UI library. I need where the initial, that means the initial HDL file will be converted into the generic technology library file, which is this design wire component. So after that, that particular design wire library, now it will be converted into the this target library. So target library, if I call that as a mylib or any other things, that it will be done during the compilation only. So there two options are there, like automatic ungrouping, or automatic ungrouping can be done in the compile ultra mode only. Automatic ungrouping means here the levels of hierarchy will be removed. Okay, so that means in one particular cells, one particular files, all the that means module, there will be only single modules. We will cover all the, that means sub modules. There will be no individual sub modules. In one particular modules, all the cells will come. So and then automatic boundary optimization, again same thing for compile ultra command, it optimizes these hierarchical boundaries, and boundary optimization is a strategy that can improve a hierarchical design by allowing the compile process to modify the port interface of lower level design. So as I said, that advanced features can be available only in compile ultra mode, whereas this DC expert follows the basic mode of DC design compiler environment. So automatic data path extraction and optimization, again it can be available only in compile ultra mode. Register retiming also, that also can be available in compile ultra mode. I think this register, what is register retiming, what is data path extraction, and how you can do this optimization, that we have already discussed. Okay, so then full compilation and incremental compilation also we have seen earlier slides. So then compile strategies. So during the compile strategy, whenever we are that means trying to do the compiling, so at that time we can we have to optimize the circuit with respect to speed power area, right? So for that reason we have set the corresponding constant. So to ensure now the part is that to ensure that partitioning is the best possible for synthesis, the quality of optimization results depends on the how the HDL description is written. So initially I said that okay, a good HDL coder That means whenever you are writing a good HDL code itself, that means helps the synthesis process to optimize the circuit in a better way. Okay. Then you have to write the constant very that means accurately, okay, so that the constant itself, whenever you are putting the constant, the optimization becomes much more that means operational on your design, so that you get a higher performance circuit after the compilation. And then you need a good synthesis library. You have to identify the multi-cycle paths and false path. What are these multi-cycle paths and false path? That will come in the static timing analysis portion. Okay. So then instantiate clock gating elements. Instantiate clock gating element means if it is required, then you have to set it that okay, for power optimization I need clock gating option, because clock gating is one of the technique by which you can optimize the power. So then optionally you can also define the scan style. That means you can put this boundary scan chain to the circuit for testing purpose. That means to make easier of this testing purpose, that also you can do. Then determine the best strategy for optimizing your design. Okay. So these things you can do. This you have to, before starting the compilation, this you have to prepare. So design specification for designs top, how you can set. So this operating condition is set as worst case, valid model as 20x20, clock frequency set as 40 MHz, input delay time is 3 nanosecond, output delay is 2 nanosecond, input drive strength is 1 volt, output load is 1.5 picofarad. So the constant file will be set. Suppose this is the specification for this top I have to meet. So now based on this specification, how can I set the corresponding constant file before compilation? So here you see set operating condition, this, set valid model as this, create clock as this. So here 40 MHz means 50 nanosecond will be the clock period. So sorry, 25 will be the clock period. So that's why this create clock period is 25. Input delay is 3, output delay is 2, maximum load is 1.5 for all outputs, driving cells is this one, then set drive 0 for clock. Okay. So that means for this particular specification, now I am setting this constant to maintain the corresponding or to achieve this specification for my design top. And I have to say that okay, in some of the case like the clock paths, if it comes or if it known as if it is comes under the critical path, so all the time the compiler will tries to reduce it. That means it will try to optimize those paths, but we don't want to touch the clock path in the circuit. So at that time what you have to do, or any path, not the clock path, suppose one path you don't want to touch, you want to be, that means that it intentionally you are putting that things, so that will remain same. So at the time what you can do, you can put this command okay, that as set don't touch. Set don't touch means, so at the time during the compilation, which module you set or which cells you set, like here you set that set don't touch U2, U3, or U2, U4. That means out under U2, U3 and U4 that will not be touched. So if you set that this command that set don't touch, so at that time underscore that means under this U2 module, this U3 and U4 sub module will not be touched. Okay. So then ungroup method. So that means ungroup method means if this is suppose U1 and U2 are this one, and I want to ungroup this U3 and U4 here. So at that time I have to write this command ungroup U3 and U4, then compile ultra, so U3 and U4 will be ungrouped. So these comments we have already discussed. So ungrouping method is this one. So architectural optimization, so there are several ways of basically architectural optimization. So architectural optimization is on the designer's hand, how he can optimize his circuit whenever here he is drawing the micro architecture of that particular circuit. So at that time he can or he or she can do the optimization there. So though there are that means the tool itself it can do, these are the basic, that means architectural optimization technique which is already included with the tool, like this common sub expressions, sharing of this common sub expression, then sharing resources, selecting the design wire implementation, or reordering the operators, or identifying the arithmetic expression for data path synthesis. Okay. So that means these are the things, this common sub expression elimination algorithm, this is very much common. So this for filter design or some of the, that means of DSP operation, this may be applied for architectural optimization to meet the specification. Resource sharing, we have already seen one of the example for resource sharing, like two adder then one multiplexer, that example we have already seen. So sharing the resources also, we can reduce the area consumption as well as for the power consumption. Then selecting the design wire implementation means actually in the design wire library there are the operators like multiplier, adders, these are already there. So just putting the star, you can you can use, or you can, that means invoke the multiplier components, design wire multiplier components from the library. So they are being fully optimized. They have like you can design a multiplier using different ways, like Booth multiplier or Baufuli multiplier, any multiplier you can design. But the multiplier which has been already there in the design wire library, they are the best, that means best in terms of area, power and timing. Okay. So that's why you can choose those, or reordering the operators, that means the operators reordering, if it is helps to reduce the area, so at that time you also can use that. And then arithmetic operation for data path synthesis you can identify, and then you can do that optimization of that. Okay. So this is architectural optimization techniques which you can do automatically in the, that are available in the DC, so that you can do. And for this today's lecture up to this one. So next day again we will see some of the optimization technique along with the rest of the part in design compiler. Thank you.